Okay, so now we're back and we're still talking about chi-squared tests and we're still talking about chi-squared goodness of fit tests, but we're going to add a little something on to it, and that is the idea of the follow-up. So we've done our chi-squared test, and let's say we reject our null hypothesis. So what we're going to do now is we're going to do that follow-up. And so if we reject our null, we can perform some sort of follow-up to determine what category are these differences really occurring. So now that we've done it, we said, hey, there's differences here. Where are those differences occurring and in what direction? So what information are we going to take from that? So that means we're going to take a look at those components. So when we were doing that chi-squared test and we calculate, okay, this minus this squared divided by this, and then plus, and so each one of these gives us a component. And the one with the largest value will actually contribute the most to the chi-squared statistic, and these allow us to figure out the size and the direction of the component from the expected values. So if we were to look at our last problem that we did in the last set of notes, I have it still programmed in my calculator, and that test was, let me take a look at it really quick. So we were looking at the proportion of people in their 20s, 30s, and 40s. So when we look at that on our calculator, take a look at that stat list, and then so here was our actual value, our observed value. This was our expected value, and then this is the chi-squared component. And so when we're looking at this, we're seeing the biggest differences in the first category and the fourth category. So this is people in their 20s and people in their 50s. And so we're seeing the biggest differences there. And so then the next question is what direction? So when we're looking at this, we're going back to those original values and we're saying, you know what? We're seeing less people in their 20s in this grouping. And then down here, we're seeing more people in their 50s than we expected. And so that's our follow-up. Where are those differences occurring? And so we're going to do the same thing in our next test. We're going to take a look at we're going to do our test, and then we're going to do a little bit of a follow-up. So for people who like stats, Malcolm Gladwell has this great book called Outliers, and he specifically talks about this situation where hockey players' birth month has a big influence on their chance to make it to the highest levels of the game. Specifically, January 1st is the cutoff date for youth leagues in Canada, where many of our NHL players come from. Now, players born in January will be competing against players up to 12 months younger. So those would be people born in December of that year. So they're almost totally 12 months, they're almost a year older than them. The older players tend to be stronger, bigger, and more coordinated. Therefore, they get more playing time and more coaching and have a better chance of being successful. Now, that was a theory. So to see if it's true, they took a random sample of 80 NHL players from 2009 to 2010. And then they looked at their birth dates. Now, overall, 32 were born in the first quarter, so the first 3 months of the year. 20 were born in the second quarter. 16 were born in the third quarter, and 12 were born in the fourth quarter. So rather than break it up by month, we broke it up by, just because we didn't want to have to deal with 12 categories, we broke it up by quarter. So we broke the year up into fourths, which is really 3 months. So now the question is do these data provide convincing evidence that the birthdays of NHL players are not uniformly distributed throughout the year? So uniformly distributed means that they're going to be equally spaced throughout the year, that there's not like a preference, like all of our good hockey players weren't born early in the year because of the way we run our hockey leagues. So we'd expect all of these proportions to be the same. So, state. we will perform a chi-squared goodness of fit test at a 0.05 significance level. And our null hypothesis is that there is no difference between them. So I'm going to take my full probability, and I'm going to divide it up between the 4 quarters, meaning that I should really have 25%, or about 25%, in each part of the year. If my null hypothesis is true, that they're evenly distributed. Now, if they're not evenly distributed, then that's our alternative hypothesis. At least one of these guys is going to be incorrect. And then we have to state, what does P1, P2, P3, P4 stand for? Well, this is our proportion of birthdays of NHL players in each quarter of the year. So our first quarter would be January to March, so that's our first 3 months, January, February, March, so on and so forth. So now we're going to check our conditions. So random, we had a simple random sample of 80 NHL players. And we did this for a specific year that they were playing in the NHL, which was 2009 to 2010. Okay, now large sample. So this is what we expect to have happen. So now we're going to go back to this idea of our HO based on our total amount of people. So we had 80 people, so we'd expect 1/4 of the 80 people, which is 20, to be born in the first quarter. So I just have to check and make sure that's greater than or equal to 5, and I do that for each one. Even though I know it's the exact same thing each time, I'm supposed to check each proportion, even if each proportion is exactly the same. So I still have to show that I am testing all 4 categories, or all 4 quarters. Those are my categories. To show that I'm just not lazy and I really do understand that I have to check every single category. So now what we're going to do is we're going to go ahead and check for independence. So independence, well, we didn't sample with replacement. So reasonable to assume more than 800 NHL players in 2009, 2010. Now, I don't know how truthful that statement is. That might be something worth just kind of looking up on the internet really quick to see how many players are usually on a hockey team, and then how many teams are there, so we can get an idea of how many people there usually are in the NHL. But usually that's something when you're setting up your thing you would check. Before you determine how many people to sample, if you're not sampling with replacement, that you're making sure that you're sampling less than 10% of the population. So if they did their stuff right, we should be okay. So then our next step is to go ahead and calculate our chi-squared. So chi-squared will be our observed. So we observed 32 in the first quarter. We're going to subtract how many we expect. And this is squared. Actually, let me fix that. This is how it should really look. So we're going to 32 minus 20, and that is squared. And then I divide by the expected. And then I calculate for the next one. So what is it? 32 and then 20 minus 20 squared divided by the statistic, or the expected. And then, oops, not equals. And then I would keep going. We only have to list out the first 2, so that's what I'm going to do. And then we would go to our calculator and we would put these values, 32, 20, 16, and 12 in our list 1. And then we'd put these 20, 20, 20, and 20 in our list 2. And then we'd use L3 to help calculate our chi-squared statistic. And so when we do this, we're going to end up with a chi-squared of 11.2. And now it's time to calculate our probability value. So our p-value is the probability that our chi-squared is greater than 11.2. So we're going to do a chi-squared CDF with a lower bound of 11.2, an upper bound of something just really, really big, and then our degrees of freedom being the number of categories minus 1. So we broke this up between 4 parts of the year. So we take our 4 parts minus 1, gives us a degree of freedom of 3. And when we calculate that, we get a 0.0107. And then from here, we're just comparing that to our significance level. So is 0.0107 less than 0.05? And if it is, we reject it. If it's not, we draw a line through that less than symbol and we fail to reject. It is less than, since our p-value is less than 0.05, we reject our null hypothesis. And we do have convincing evidence that at least one of the proportions for people born in each quarter of the year in the NHL is not equal, that's supposed to be not equal, throughout the year. So now it's time to do our follow-up. So now we're going to look at, we concluded that they're not uniformly distributed throughout the year. However, the claim wasn't just the distribution wasn't uniform. He specifically claimed that NHL players are more likely to be born early in the year. Use the values for each component to discuss this claim. So let's take a look at those components. Okay, so let's look at those components here. And when we look at those components, we can definitely see that we have a really high component at 7.2 from the first category. We have a 0, which is right on, a 0.8, which is really close, so it's not that big of a deal, and a 3.2 here. So my biggest contributions to our chi-squared is the first category and the second category. So then we go back and we analyze those differences. So here we can see that the first quarter is a lot higher than we expected, and our last quarter is a lot lower than we expected. And so we can use that to describe what's happening in our follow-up. And so now we say the first quarter has the largest component. So we're saying that it has the largest component, so it makes the biggest change, the biggest difference in what we expect, and it's in the direction of being higher by having a higher value than expected. Now, the fourth quarter has the second largest component, by having a lower value than expected. And this supports Gladwell's claim. So again, just using that, okay, there is really statistically a difference here. So now, where is that occurring? Okay, is that supporting what he's saying is truly happening in this situation? And it is.